Alrighty, section 4.1, we're going to talk about functions and whether they're increasing or decreasing at a certain area, or concave up or concave down at a certain area. Alright, let's start out by talking about what it means to be increasing or decreasing. Take a look at that picture. There's a lot of stuff going on. What if I told you that we can just look at the original function and determine if something is increasing or decreasing at a certain area by taking its derivative? How do we do that? Well, if the derivative of a function is positive, that means that at that moment right there, the original function f of x is going to be increasing. So that means if I were to have a positive derivative at, in this case, 5, my function is increasing. If I were to take the derivative of a function and at a certain time my derivative is negative, I have a decreasing function. So it could either look like that, which is a slope of -1 that looks like, or maybe it kind of curves down like this picture right here. That's an example of a decreasing function as well. Well, what if I take the derivative and I have a 0? What's happening then? Is it increasing or decreasing? Well, as a matter of fact, neither. It's constant. Constant means it's a horizontal line. So you have one of 3 options. That's the third. Let's find out how we do it. All right, so these are going to be the steps into finding whether a function is increasing or decreasing at an interval. All right, step number 1 is you're going to take the derivative of that function. All right, step 2 is you find the zeros. That means you set the equation equal to 0. Usually you do some type of factoring, and you find out the x values that make your function equal to 0. Look up zero product property if you have a hard time figuring this part out. Then you're going to substitute a number within the interval, which means you're going to figure out a number that's not a critical point, plug it into the derivative, and see if you get a positive or a negative. That'll determine if you have increasing or decreasing. Once you know which intervals are positive or negative, you can use that determination to figure out where your original function f of x is increasing or decreasing. Alright, for this one we are to find the intervals where the following function is increasing or decreasing. We're going to have to do some factoring here. And let's just get to it. First off, I have to take the derivative. So the derivative of f of x is going to be equal to negative 5x to the 4th. Drop down the 5, take away 1. Drop down the 4. 5 halves times 4 is going to be 10. X to the 3rd. Drop down the 3. That kills off the 3 there. 40x squared. And then plus 5 goes away. Now, as you remember from the previous slide, after I take the derivative, my job is to find the zeros rather. What that means is I take this guy and set it equal to 0. Okay, now the way I find the zeros usually is by factoring. So let's factor as much as we can. Looks like we can factor out quite a bit. I'm going to factor out not only just a 5, but a -5 because I usually want my leading coefficient to be positive after I factor things out. I'm also able to take out 2 x's, so -5x squared comes out. After I factor that out, after I take -5x squared out of -5x to the 4th, I'm only left with 2 x's. After I take a -5 out of +10, I'm left with a -2 because I'm taking a negative out of a positive, which leaves me with a negative. I'm taking 2x's away from 3x's, and that's what leaves me there. And I'm taking a -5 out of positive 40, so that leaves me with a -8. I'm taking 2x's from 2x's, which leaves me with no more x's. All right, so that's part one of factoring. I'm not quite done factoring yet. -5x squared. I need to come up with two numbers whose sum is -2, whose product is -8. One's going to be positive, one's going to be negative. And it looks like 4 and 2 should do it. Now, 2 is going to be the positive one, and 4 is going to be the negative one, because if it were vice versa, that would be a positive 2. Because if I add -2 and, positive 2 and -4, that gives me the -2. If this was positive and that was negative, that would be positive, which is not what I want. So the last step in finding the zeros is I have three factors, 1, 2, and 3. I set them each equal to 0 and find out what my x's would be. So if I were to say -5x squared equals 0, this is all stuff you learned back in probably Algebra 2, maybe Algebra 1, I don't know, back in the day. Set all three of those factors equal to 0. I'll do this quick. If I divide by -5, I get 0 still. If I take the square root, positive or negative square root, I still get 0, so I have a 0 here. If I were to subtract 2, I'd get -2. And if I were to add 4, I'd get +4. All right. So those are what I like to call my critical points. Critical points. I have 3 of them. Now what I have to do is I have to figure out the intervals in which this is increasing or decreasing. These 3 numbers tell me that there's going to be a change in increase and decrease. So what I'm going to do is I'm going to make an F prime number line looking thingy. I'm sure that's what the math teachers call it. My smallest critical point is -2, so I'm going to put a -2 right there. My middle critical point is 0, and my largest critical point is 4. Okay, it's not going to be inaccurate as far as the drawing goes, but what I need to do is I'm going to have an interval of everything smaller than -2, everything in between -2 and 0, and everything in between 0 and 4, and everything greater than 4. So what I need to do now, and this was step 3 from the previous slide, is I need to substitute a number within the interval into the derivative to find the sign. So when I say find numbers within the interval, like a number that I can choose anything smaller than -2, how about -10? Anything in between -2 and 0, how about -1? Anything in between 0 and 4, how about +1? Anything greater than 4, how about 10? Okay, what I need to do now, again, is I need to plug in these numbers that were within the intervals into the derivative. Okay, so if I start out by plugging in -10, f prime of -10 is going to equal -5 times -10 to the 4th, plus 10 times -10 cubed, plus 40 times -10 squared. Okay, all I need to do is the number doesn't matter. The sign is all that matters. So if I do that, I get -10 to the 4th, which is it's positive. -5 times positive 1, 2, 3, 10,000. Could have probably picked a better number, but oh well. Plus 10 times -10 to the 3rd, which is going to be -1,000. Plus 40 times 100. 40 times 100. And I'm pretty much going to stop right there. -50,000 minus 10,000 plus 4,000 is going to end up giving me a negative number. So right there, I already know that it's negative. I'm not going to go crazy figuring out what the number is. Let's face it, I don't even have a calculator on me. So I know it's negative. Trust me. Let's plug in -1. F prime of -1 means I do -5 times -1 to the 4th plus 10 times -1 to the 3rd plus 40 times -1 squared. -5 times -1 to the 4th is going to be 1, plus 10 times -1 to the 3rd is going to be -1, plus 40 times -1 squared is going to be 1. So I have -5 times 1, which is -5. I have 40 times 1, or let's just go in order. -5 minus 10 plus 40 is going to end up being 25, which is positive. Okay? Next number to plug in is regular 1. -5 times regular 1 to the 4th plus 10 times regular 1 to the 3rd plus 40 times regular 1 squared is going to end up giving me -5 plus 10 plus 40. I already know that 1 to the anything power is just going to be 1, so I'm not going to go crazy racking my brain. Oh, look, another positive. You thought it was going to be back and forth, didn't you? Well, it wasn't. Tricked you all. Let's plug in 10. F prime of 10 is going to equal -5 times 10 to the 4th plus 10 times 10 to the 3rd plus 40 times 10 squared. Okay? That's going to be -5 times 10,000 plus 10 times 1,000 plus 40 times 100. All right. You ready for this one? -5 times 10,000 is -50,000. Plus 10 times 10,000, or I'm sorry, that should be 1,000. -5 times 10,000 is -50,000. 10 times 1,000 is 10,000. Okay. So I already have negative is more powerful by a lot. Let's just write it down. -50,000. I don't know why I'm doing too much in my head. Plus 10,000 plus 4,000, right? Okay. These two will combine. That's pretty big, and that's not as big. So I'm going to get 14,000 and -50,000. That's going to stay negative. So this is what this means. Okay, I'm going to go back to my number line all this time later. 5-minute problem. I'm not even done yet. This is negative right here. This is positive right here. This is positive right here. And this is negative right here. Okay? After I write all of that out, I'm using those signs and I'm using those negatives, positives to determine which is increasing or decreasing. So I have two sections in which my line is decreasing. And I have two sections in which my line is increasing. According to the numbers that I have, it's decreasing for everything less than 2. So I will say it's decreasing when x is less than 2, increasing, and it's increasing when x is greater than 4. Why am I not including the zeros, or the equal to's, I mean? Well, because it's neither negative nor positive at -2. These guys, if you remember from the previous slide, when it is 0, it's constant. So at these 3 points, at the critical points, it's constant. And if you remember from the pictures, constant means it's a straight line. But in these cases, it's only happening at these spots. It's not a line at all. It's just basically changing. It's just going... We're not going to worry about that. It's also increasing here at -1. Well, in between, rather, -2 and 0. So we're going to say it's increasing when x is in between -2 and 0. And it's also increasing in between 0 and 4. So everything smaller than 2 is negative decreasing. Anything in between -2 and 0 is increasing. Anything in between 0 and 4 is increasing. And anything bigger than 4 is decreasing, just kidding. All right, breathe that in. Breathe it in. It's a lot. All right, before we go any further, let's talk about what it means to be concave up and concave down. Concave up means your graph looks like a U shape. It's usually decreasing and then increasing. If it's concave down, it's an upside down U shape, which means it's increasing and then decreasing. So this process is pretty similar to the first one that we did. If you take the second derivative, plug in a point on the interval, and you get a positive, your graph is going to be concave up on that interval. If you take the second derivative, plug in a point in the interval, and you get a negative answer, that interval is going to be concave down. When you take the second derivative and you get 0, that's when concavity changes. Those areas are called inflection points. So you see that regular U turn into an upside down U, or vice versa. Okay, buckle your seatbelts. We're to find the intervals where f of x is not only increasing or decreasing, but also concave up and concave down. So if you remember, increasing and decreasing is a 4-step process. Step number 1, take the derivative. 3x squared minus 6x. Okay, find the zeros. Set it equal to 0. And just like in the last problem that we did, usually we have to factor out. So not only can I factor out a 3 from both of them, I can factor out an x. Once I do that, that leaves me with x minus 2. Why x minus 2? Because if I pull a 3x out of a 3x squared, I'm only left with an x. If I pull a 3x out of a 6x, I'm only left with a 2. I set each of these equal to 0. Easy math. Okay, divide by 3, x is going to equal 0. Add 2, x is equal to 2. So these are my critical points. I'm going to call them CP. Okay, and what I'm going to do is I'm going to split this in half so I can spend the right side doing the second derivative stuff. We'll get there when we have to get there, but we're not there quite yet. Okay, now what I have to do is I have my critical points, so I'm going to create that number line looking thing for my derivative. Okay, my critical points are 0 and positive 2, so I'm going to end up plugging in, I don't know, negative 1, regular 1, and 3. Okay, last time I picked like 10 and I immediately regretted that. Sometimes that's convenient, but in that case it really wasn't. All right, let's plug them in and see what sign I get. F prime of negative 1 is going to be 3 times negative 1 squared minus 6 times negative 1. Okay? 3 times negative 1 squared is 1. Minus 6, minus 6 times negative 1 is going to be plus 6, positive. Okay? 3 plus 6 is 9. Let's plug in 1. 3 times 1 squared minus 6 times 1. 3 times 1 is 3, minus 6 is going to be negative 3, so I got a negative there. Okay. F prime of 3 is going to be 3 times 3 squared minus 6 times 3. Okay, 3 times 9 is going to be 27, minus 6 times 3 is going to be 18, positive. Okay, so in this problem, I can say that I'm really bad at writing and talking at the same time. But I can also say that since it's positive, negative, positive, positive, negative, positive, that means that this right here is increasing, that's decreasing, and that's increasing. I forget what I said in the last problem. I forget if I actually wrote out increasing, decreasing. No, I didn't. I wrote out negative and positive. But this positive means that everything from 0 down is increasing. Everything from 2 up is increasing. And everything in between 0 and 2 is decreasing. Okay? That's part 1. Part 2 is concave up and concave down. All right, so the increasing, decreasing part, donezo. Concave up and concave down involves me taking this guy and taking the second derivative. So if I take, and I'm just rewriting f prime right now, all I'm doing is rewriting it out. If I take the derivative of that, I get my second derivative. The derivative of 3x squared is going to be 6x, and the derivative of negative 6x is going to be minus 6. Okay, just like last time, I find the zeros. I factor out what I can factor out, which is just a 6. Okay, I set each factor equal to 0. This is impossible, so it won't work. Add 1. And I only have one guy. And these guys, right here, well, this guy, in this case, is called my inflection point. Now I'm going to do the same exact thing that I did here, but with an f double prime line graph. I have 1. So I can plug in 0, I can plug in 2. And I'm going to plug in 0 and 2 into my second derivative. I'm going to plug in 0 into my second derivative. Okay, so f double prime of 0 is going to be 6 times 0 minus 6, which is going to be 0 minus 6, so I get a negative. If I plug in 2 into my second derivative, I give up. I get 6 times 2 minus 6, which is 12 minus 6. That gives me positive. Now, when the second derivative is negative, that means it's concave down. When my second derivative is positive, that means it's concave up. So I have concave up. I have concave down. It's going to be concave up whenever my interval is positive. This was negative. This was positive. Okay? So concave up is going to be everything greater than 1. Just like in the last problem that we did, we're not going to include 1 because at 1, x double prime or f double prime is 0, and that's when the concavity changes. And when the concavity changes, perhaps you should go to the dentist. Okay. But anyway, never mind. When x is less than 1, it's when it's concave down. All right. What's going to be really fun is in a few sections when we actually sketch graphs that look like that. So, never said it was easy. I only said it would be fun. Take that, pause it, rewatch it, do what you got to do. But I believe that's the only problem we're going to do in this chapter, and then homework, which is coming up next. Bye!